Okay, good evening friends. Today we shall be discussing about relationship between real and imaginary parts of DTFT, that is discrete time Fourier transform. Now, in your earlier courses on DSP and signals and systems, you must have studied something about discrete time Fourier transform of sequences, discrete sequences. So, in this subject advanced DSP, we will start off with this particular topic. Before we go to the subject proper, I will just cite a few examples in the continuous domain that you have studied probably, or you those who have done design of analog circuits with passive elements, they must be conversant with this. I will just brush through some of the basic elements of those functions. Now, suppose ZS is a network function, corresponding frequency domain response is Zj omega. We shall be using capital omega for analog frequencies and small omega for discrete frequencies. That is, small omega will have radians as units and omega will be the normal one, radian per second, that you are conversant with. Okay. Now, this can be written as a real part and an imaginary part. Okay. Or we can write in the polar form in magnitude and phase. So, to describe ZS, we need the information both real and imaginary parts. All right. Now, is it possible to obtain the network function if you are given only part of it, either the real part or the imaginary part? For example, I have a resistance and an inductance, okay, say resistance of 10 ohms and an inductance of 1 Henry. What will be ZS? It will be 10 plus S. What will be its real part? It is only 10. Now, if I have another circuit with an inductance 2 Henry, then Z is the real part, ZS is 10 plus 2S and a real part of Zj omega is still 10. So, from here in these two cases you are having the same real part, but the network functions are different. So, there is an ambiguity. Okay. So, we can design, we can evaluate those functions which will be having just the minimum number of elements as a reactive element. We call it minimum reactance function. Minimum reactance for the realized network will be possible. That means, we find out a network function. I have taken a very simple series element, it could have been much more complicated. So, given the real part, you can realize the imaginary part, where the imaginary part realized will be having minimum reactance value. Anything you add any more reactance, the real part does not change. Conversely, if you are given the imaginary part, then you keep on adding more resistances, but the imaginary part will not change. So, we can design only, we can evaluate only a minimum resistance impedance function, an impedance function which has minimum resistance. All right. I will just give you an example of how to evaluate this, a simple method, then we will go over to other areas. For example, the real part will correspond to an even ZS at S equal to j omega. Okay. The even part corresponds to the real part and the odd part corresponds to the imaginary part, is it not? So, even ZS, if we can evaluate, suppose ZS is written as some polynomial, okay, Ps by Qs. I can write Ps in terms of an even part and an odd part. Similarly, even part and an odd part. Okay. So, even ZS will be even part of this, which can be written as M1 plus N1s. If I multiply by M2 minus N2, then denominator will be M2s squared minus N2s squared. Okay. Sorry. So, even ZS will be even part of this function. This is ZS, all right. ZS, the denominator has been converted into an even function. See, M2 square minus N2 square is an even function, because this is odd function square, it is an even function. So, the denominator is an even function. So, the even part, therefore, even ZS, that is even part of this, can be written as M1 M2. If you permit me, I will not write argument S anymore, minus N1 N2 divided by M2 square minus N2 square. Okay. And M1 N2 N1 M2, that will correspond to the odd part. M2 square minus N2 square for any value of S equal to j omega will always remain positive. Why? M2 square minus N2 square is always positive. Why? M2 plus N2, if I put S equal to j omega, will be say something like A plus JB. Okay. Then what will be M2 minus N2? It will be A minus JB. It is the odd part only which will be having a change in sign. The even part, omega square, omega 4, etc. If you put omega equal to minus omega, then also they will remain positive. Okay. So, it is only the odd part which will be changed, which will be having a different sign. So, if M2 plus N2 gives you A plus JB, then M2 minus N2 will give you A minus JB. So, M2 plus N2 into M2 minus N2 is A square plus B square, that is always positive, it is a magnitude squared, alright. So, we have to check whether this quantity is positive or not, then only the real part, the even part, okay, will be always positive. So, if you are given a real function, a real part of z j omega, okay, if that is given, say let us take an example, it will be clear, is given as 1 plus omega to the power 6. Okay. That means, if I put omega is equal to S by j, S equal to j omega, the inverse substitution will be omega equal to S by j. Alright. So, from the given function in the frequency domain, if I want to get back to S domain, I will just replace omega by S by j. So, what does it give me? That gives me the even ZS equal to 1 by 1 minus S to the power 6. Okay. If I substitute this, omega is equal to S by j, so S by j to the power 6, that gives you minus S to the power 6. 1 minus S to the power 6, what are the roots? S to the power 6 is equal to 1. So, S is 1 means e to the power j 2 pi k. Okay. So, this will be e to the power j 2 pi k by 6 into 1. So, you keep on taking different values of k, it will be on a unit circle. K is equal to 0, k equal to 1, 60 degrees, k equal to 2, k equal to 3, k equal to 4, k equal to 5 and 6. 1, 2, 3, 4, 5, 6. There are 6 roots. Now, for a stable system, if ZS is a realizable network, all the roots of the denominator should lie in the left half plane. I know this ZS that we have got, that is M2 plus N2 and M2 minus N2. If M2 plus N2 is to correspond to set of stable roots, then that must correspond to these 3 roots, and M2 minus N2 will be giving you the mirror images. So, once you have decided, once you have calculated all the roots, take away only the left half plane roots, right half plane roots are just the mirror images. Okay. So, taking the left half plane roots, you can form the polynomial. What are the roots? What will be the polynomial? 1 by the denominator polynomial will be 1 is corresponding to minus 1. So, s plus 1 is a factor. Okay. The other one will be, this is 120 degrees. So, this is 60 degrees. So, cos 60 is half, this is minus 0.5 plus j point root 3 by 2, j root 3 by 2 minus j root 3 by 2. So, it will be s plus half plus j root 3 by 2 into s plus half minus j root 3 by 2. Arising out of these 3 roots, the corresponding polynomial will be this. Okay. So, this is the denominator, which means M2 plus N2, is it not? We have started off with the roots of M2 square minus N2 square. There are 6 roots. We know M2 plus N2 will give me these 3 roots, M2 minus N2 will give me these 3 roots, okay, because it is a stable system. So, the roots correspond to this must be these 3, and these are the polynomials, all right. If that be so, then let us go back to our original function. Zs therefore can be written as, this can be written as, if you simplify this, it will be s cubed plus twice s squared plus twice s plus 1. Okay. You just multiply and then multiply by s plus 1, it gives you this. So, this is the denominator polynomial. Okay. So, our Zs is sum a0 plus a1s plus a2s square plus a3s cubed divided by s cubed plus twice s squared plus twice s plus 1, because we have been able to identify the denominator m2 plus n2, okay, from the given function. So, if you segregate again the real and the even and odd part, this is a0 plus a2 s squared plus s into a1 plus a3 s squared divided by again 1 plus 2 s squared plus 2s plus s cubed. So, this is m1, this is m2, this is sorry, this is m1, this is n1, this is m2, this is n2. Okay. So, I have identified m1, m2, n1, n2. However, these coefficients are not yet known, all right. Now, you try to find out what is the numerator of even ZS, that should be M1 M2 minus N1 N2. This is the even ZS. The numerator part, this is already known. The numerator part, what was given as 1, numerator corresponds to 1. So, try to match the numerator. Now, what is M1? This one. So, A0 plus A2 S squared M1 into M2, 1 plus twice S square minus N1 S into A1 plus A3 S squared into N2 twice S plus S cubed. Okay. That should match with that numerator given, that is 1. Okay. Is it not? This is the numerator M1 M2 minus N1 N2, and that should be equal to 1. So, now by matching the coefficients of S squared, S equal to j omega, okay, by matching the coefficients of omega, you can get all the coefficients. Okay. If you can write it, A0 into 1, so A0 comes out to be 1. All other coefficients of S square, S4 etc. will be 0. What will be the coefficient of S square, for example, and S to the power 4? We have up to S to the power 6. So, there will be 3 equations, S to the power 2, S to the power 4, S to the power 6, 3 more equations, all the coefficients are equated to 0. So, the equations are, you can check up, twice A0 minus twice A1 is equal to 0, then twice A2 minus twice A3 minus A1 is equal to 0, and A3 is equal to 0. See, A3 into S square into S into S cube. So, A3 to the power into S to the power 6, and there is no S to the power 6 term. So, A3 is 0. Substitute it there, and A1 you substitute, A0 you substitute here. So, you get 2 equations in A2 and A1, solve them, you get all the coefficients. So, I will write finally the ZS as two-third S squared plus 4 by 3 S plus 1 divided by S cubed plus twice S squared plus 2S plus 1. This is a very simple technique of evaluating the network function given, say, the real part. Okay. We have also seen in frequency plots, say when you are given the Bode plot of a system, suppose a network function is given in this form, 1 plus S by A1 into 1 plus S by A2 and so on, divided by 1 plus S by B1 into 1 plus S by B2 and so on. Okay. How do you make a Bode plot? You take individual components, all the numerator functions will have the appearance like this, 20 dB per decade. This is at A1, this is at A2 and so on, and the denominator functions will be having 20 dB per decade fall at B1, B2 and so on. Okay. Now, if there is a mix up and if they are reasonably separated, then the total, the asymptotic plots if you make will be it may be given to you, the asymptotes may be So, maybe like this, the gain plot, dB gain, that is 20 log of g, this is the frequency plot. Now, since these are asymptotic plots, the exact plot may be somewhat like this. We are not bothered about the actual plot. The actual plot has been decomposed into approximate straight lines with 20 dB or 0 dB or minus 20 dB slopes or multiples of 20 dB. Okay. So, with these clearly separated frequencies, you can see there is a rise here. This corresponds to a term like S in the numerator. Then there is a break, 20 dB per decade fall has been added here. So, corresponding to this frequency, say 1 by T1, there is a fall here. So, that will be appearing here as 1 by S plus T1 or B1, whatever you call it. Similarly, here there is a rise. So, 1 by T2 will appear as 1 plus S by T2 and so on. This is how you realize from a Bode plot. From the sketch you can realize the network function or the gain function, system transfer function. Okay. Now, from the gain plot, can you estimate the phase? Once you have estimated these, for each component, you know if there is a factor, say 1 plus S T by 1, suppose it is in the numerator, it can be in the denominator also. What is the phase contribution of this particular factor? At this frequency, I should have written T1 into S, dimensionally it should have been T1 into S, T2 into S. Okay. So, that 1 by T1 is the frequency, I am extremely sorry, it should have been T2S, T1S. So, 1 by T1, 1 by T2, these are the corresponding frequencies. Okay. Now, T1S. So, at 1 by T1, how much is the angle? It is 1 plus J1 at a frequency S equal to J omega, at omega equal to 1 by T1, this becomes J. So, 1 plus J, that is 45 degrees. This is what you do in Bode plot, is it not? At that particular corner frequency you have 45 degrees, 1/10 the corner frequency you have an angle of approximately 6 degrees, and 10 times that you have about 84 degrees, and then some intermediate points you calculate. So, you get a profile, okay. You have a profile, thank you, like this. Either this is that frequency at which the change is taking place, this corresponds to 45 degrees. 10 times that, that is 10 by T1, it is about 84 degrees, and 1/10 of that, it is about 6 degrees. So, you get a profile like this, and you can keep on using this as a stencil, you can keep on shifting it, fix this point at 1 by T1, 1 by T2, 1 by T3, you can reverse it. If it is in the denominator, the phase function is like this, just an image of this, a mirror image of this. Okay. Okay. So, this is corresponding to a factor 1 by 1 plus ST1, and this corresponds to 1 plus ST1 in the numerator. So, once you are given a gain function, you can resolve it into approximate asymptotes and then find out the frequencies and hence their nature, whether they will be appearing in the numerator or in the denominator, and accordingly you can construct the contribution of phase for each component. For each component you can see the individual component of phase, add them together, you can realize the phase function. Okay. Or once you have realized the network function, you just put s equal to j omega here, s equal to j omega, and then find out theta omega, theta as a function of omega. Okay. You can do either way. Now, based on this, we will now try to see whether it is possible to derive any relationship between the real part and the imaginary part of a complex quantity, that is the frequency response, discrete time frequency transform DTFT of a sequence normally we write e to the power j omega of a real sequence xn. Okay. Now, this Bode plot, before we start here, one more point I would like to mention. If you have a function like 1 minus st1 by 1 plus st2 and 1 plus st1 by 1 plus st2, you will find the magnitude functions will be same for both of them. Magnitude will be same for both of them, is it not? So, from the magnitude you cannot really evaluate the phase unless there are certain restrictions imposed on this. That is, we would like to realize only those functions which have roots in the left half plane, that is the zeros also should be included in the left half plane. If that is so, then only we can realize this. It is not unique otherwise, it can be either this or this, alright. Even if it is stable, the denominator will be 1 plus st by st2, I cannot put 1 minus st2, then it will become unstable, but even for a stable system it can be either minus or plus. So, when it is all roots in the left half plane, that is both poles and zeros are in the left half plane, we call it a minimum phase system. So, we can realize only minimum phase system like minimum resistance, minimum reactance functions we were discussing earlier for network functions. Similarly, for a transfer function from Bode plot we can realize only minimum phase system. Now, let us see in the discrete domain an identical nature of ambiguity. If I have a function 1 minus 2 z inverse by 1 plus 0.4 z inverse and another function 1 minus 0.5 z inverse by 1 plus 0.4 z inverse. Okay. Now, this I can write as 1 minus 0.5 z inverse by 1 plus 0.4 z inverse into 1 minus 2 z inverse by 1 minus 0.5 z inverse. I have just multiplied by this factor 1 minus 0.5 and divided also by the same factor. Okay. Now, what is this? It is the second function, alright, is equal to, I call it say h1 and this as h2. So, this is nothing but h2 into 1 minus 2 z inverse by 1 minus 0.5 z inverse. Now, let us see what is the frequency response of this, what is the discrete time Fourier transform of this. You put z is equal to e to the power j omega, is it not? So, let us see 1 minus 2 z inverse by 1 minus 0.5 z inverse equal to 1 minus 2 into e to the power minus j omega by 1 minus 0.5 into e to the power minus j omega. Okay. Now, we would like to see what will be the magnitude of this. What is the magnitude of this function? Okay, let us call this as some g. So, we are interested in finding the magnitude of g. It will be 1 minus 2 cosine omega, is that all right, squared plus 2 sin omega squared divided by 1 minus 0.5 cosine omega squared plus 0.5 sin omega squared, correct me if I am wrong, whole thing under root, is it all right? Simplify, let us see, this is 1 twice cosine omega squared, that is 4 cos squared omega, 4 sin squared omega will give me 4, minus twice AB, so 2 into 2 4 cosine omega, okay, and here I get 1 plus 0.5 squared, that is 1 by 4 minus 2 into 0.5 into cosine omega, multiply the denominator by 4 and numerator by 4. So, that gives me 1 plus 4 minus 4 cosine omega, sorry, this whole thing square rooted divided by 4 plus 1 again 5 minus cosine omega. So, they will get cancelled. So, this is only 2, it is a constant, all right. So, the first function is nothing but the second function multiplied by a constant, all right. So, far as the frequency response, the gain is concerned. So, when you see the gain plot, when it is normalized, then we can't identify which one is what, because both of them will have the same frequency response, okay. So, this ambiguity once again can be resolved only when we consider the roots for a discrete system, roots very similar to your continuous domain, we consider the roots within the unit circle. Now, for the first function, what are the roots? Poles are identical, all right, poles are identical, 0.4 minus 0.4 and minus 0.4 in both the cases. So, this is the unit circle, it is not very much to the scale, this is other unit circle. Now, in one case, in the first case, where is the 0? Z is equal to 2 and here Z is equal to 0.5. So, 0 is at 0.5, in the other case it is here outside. So, when poles and zeros are included within the unit circle, we call this a minimum phase system in the discrete domain, all right. So, we can realize, we will try to realize only those functions which will be of minimum phase nature, okay, because otherwise there can be any number of such functions giving you the same frequency characteristics for the gain function. Now, we will take a causal sequence. Xn, any causal sequence, causal or non-causal, any sequence I can write as an even part and an odd part, Okay. Basically they are even functions and odd functions, where the even part will be evaluated from the value of the function in the positive and negative region of n. Similarly, the odd part will be x n minus x minus n divided by 2. We are considering only real sequence at this moment. Okay. If it is causal, then x minus n will be 0. Causal sequence means it will be only on the right side of the x axis. So, from here can you, okay, I will write it later on. Let me draw some sequences, it will be then clear. Suppose I have a causal sequence like this. Let us take some values. X0 is say 2, then 1, then minus 1, then 2. Just for example, I am taking a sequence like this, rest are all 0. What will be the even part? This is x n. What will be the even part? X n plus x minus n divided by 2. So, this is 0. So, 1 plus 0 by 2. So, here it will be halved 0.5. Then here it will be minus 1 and 0 divided by 2. So, minus 0.5. Okay. And then this one, so this one was also 2. So, this one also will be 1. Rest are all 0. What about the central value? Should it be 1 or 2? Yes, 2. Okay. Because there is nothing like plus 0 and minus 0. Now, from here can you establish a relation? Okay, let me complete the odd part also, then we will come back. What will be the odd part like? Now, even part, though we are defining in this side, even part means there is a replica on the other side. That is not necessarily to be shown every time, but actually it exists up to this point. Okay. This is the even part. Odd part similarly, these are all 0 valued. Odd part, what will be the odd part? This minus 0 by 2. So, 1 minus 0 by 2 will be again 0.5, then minus 1 minus 0 by 2. So, minus 0.5 and then 1. Okay. And then what will be its replica on the other side? It will be double image. Okay. So, you take image about the y axis, then again about the x axis. So, it will become minus 0.5 plus 0.5 and minus 1, rest are all 0. Okay. So, this is the odd part. We shall keep this in front of us to write x n now in terms of x e n. Now, x n, if I just multiply x e n by 2, I will get these values except the first one, is it not? If I multiply this by 2, I will get rest of the values, that is for not n not equal to 0. So, x n I can write as 2 times xen into un. If I multiply by un, that means if I multiply 2 times un, the even part is having non-zero values on the left hand side. Similarly, odd part, though the original sequence is having 0 values on the left hand side. Okay. So, unless I multiply by un, this will also be multiplied. If I multiply by 2 this function, then everything will be doubled. So, I have to multiply only this part by 2. So, I have to also multiply by un. Okay. Then what is left? This twice, here it is 2. So, whatever is the value here, that has to be subtracted, because when I am multiplying by un, I have already taken it. When I am multiplying by 2, I have taken 2 times this. So, one value has to be subtracted. So, minus x at 0 into delta n. Is that all right? Similarly, xn in terms of odd function also, if I multiply by 2 and again further multiply by un, I get all these terms except the first value. So, xn will be 2 times x odd n. Mind you, x at 0 is same as xe at 0, is it not? Even part gives me the same value at x equal to 0. Okay. Other values are halved, but this value is same. So, x at 0 is same as xe at 0. Okay. So, while subtracting it, I can also subtract xe at 0. That means, if xe is known, the complete information is given to you for realizing xn, whereas for odd functions the first value is missing, because I do not have any knowledge about the first value from the odd function. So, here minus x 0 into delta n, it should be plus, all right. So, whereas from the even part I can realize the original function, from the odd part I can realize only the non-zero values of, for non-zero values of n not equal to 0, I can realize this. Okay. It will be only this much, but for realizing it completely, that is at the initial value, I must know the initial value of the function. Now, we will start from here. The real part of a DTFT of any function, any sequence xn, okay, the real part corresponds to the even part of xn, all right. Real part will be corresponding to the even part of xn. You can see for yourself. There are proofs given, or you can prove it, and the imaginary part corresponds to the odd part of the function. So, if you are given the real part of the DTFT, that is the frequency response of the discrete system, you are given only the real part, this function, then how do you realize the odd part or the total function, total x? Total x is xr plus j times xi, this plus this, is not. So, if you are given this, how do you realize this, or how do you realize this? Fourier transform of the even part is xr e to the power j omega, we have also observed the Fourier transform of odd part is the imaginary part of the Fourier transform of the sequence. So, if we are given the real part of the Fourier transform, how do we get the imaginary part? If we know, if we can find out a mechanism of directly finding it from the real part, that is the best. Now, the logic is the real part will give me in the time domain the even part, and from the even part we can reconstruct xn, and from xn we can obtain the odd part, and from the odd part we can find out the imaginary part. Now, is it necessary to go through all these exercises, that is obtain from the real part the even component, then from the even component generate the original sequence xn, then from the original sequence generate the odd sequence, and from the odd sequence again go back to the imaginary part. Let us see whether we can skip this. Now, Fourier transform of un, okay, small un we are writing, is capital U e to the power j omega. Now, it can be shown that this is equal to pi delta omega minus 2 pi k plus k varying from minus infinity to plus infinity plus 1 by 1 minus e to the power minus j omega. Mind you, if it is just a series of ones, it would have given me this result, but since this is not an absolutely summable series, so the Fourier transform, the normal Fourier transform is not possible. Anyway, so that is why this additional term comes. When you take the Fourier transform of only this series, this is the sum in the normal case. So, we get basically a sequence of impulses in the frequency domain, impulses delta k minus 2 pi omega minus 2 pi into k, okay, this multiplied by pi. So, this magnitude is pi. It is this infinite sequence which will come as an additional term apart from this summation. Now, 1 by 1 minus e to the power minus j omega, that gives me, you can very easily resolve it, multiply both sides by e to the power j omega by 2, numerator and denominator, you will get finally j cotangent omega by 2. Okay. I leave it as an exercise, you can do this. Therefore, what will be our x e to the power j omega? So, let us write this as the Fourier transform of xn, which means Fourier transform of xn, you know, in terms of xen, twice xen minus x0 delta n. So, if I do that, the Fourier transform of this, if I write, then it will be 2 times xr, now 2 times xen into un, this is to be multiplied by un. Now, if they are in a product form in the time domain, so in the frequency domain we will get a convolution of xr, which will be u e to the power j omega minus theta d theta, okay, minus pi to plus pi. This is for the first part, for this part cotangent theta and minus x of 0 x of 0 will come, because this x 0 into delta n, if I take the Fourier transform of delta n, that is 1. So, it will be coming as a constant x 0, and if you see, this is half j or cot omega by 2, which has given me this, and there is a term half, separate half, and also a term like this. These two will generate, they will get cancelled. So, they will generate nothing extra. So, if I can write in the final form, it will be 1 by pi minus pi to plus pi xr e to the power j theta u e to the power j omega minus theta d theta minus x 0. So, 2 pi and the 2 got cancelled. So, finally, if I now substitute the values of this function, which was giving me this, I finally get e to the power j theta half minus half j cotangent omega minus theta by 2 d theta minus x 0. So, finally, the relationship is, so this is nothing but this one, first part, if you see, this will be 1 by 2 pi xr e to the power j theta and integrated over this. So, that will give me xr. Now, you can simplify this, you can see xr e to the power j omega plus j times xi e to the power j omega is x e to the power j omega, is it not, and x e to the power j omega is also this term. Now, this is generating an xr term, all right. So, finally, what you get, x imaginary part will come on this side. So, x imaginary part j omega, if you just equate, expand this and equate with this, xr will get cancelled, one xr will be inside. So, you will get xi in terms of xr as 1 by 2 pi minus pi to plus pi xr e to the power j theta cotangent omega minus theta by 2 d theta. Similarly, from starting from the imaginary part, that is starting from the odd function in the time domain, if you take the Fourier transform, then going by the same logic, we can get xr is equal to x 0. There is only one additional term to be written when we go from the imaginary part, xi e to the power j theta cotangent omega minus theta by 2 d theta. The expressions are almost identical, except that in case of imaginary part, you have only xr term, in case of real part there is an additional term, except that there is nothing else. So, thank you very much. We will be using it in the next class for the discrete domain relationship.